on the number of empty seats in the lecture hall. So you should have an easier time finding seats now. Today, I've got a few minutes of finishing up of splay trees, and then we'll move on to our next topic. So if you remember last time, we spent our hour and a half looking at splay trees. We showed that they had an amortized order log n access time and an amortized order sum of minus pi log pi access time, and also an order log of last access time, amortized cost, and a few other things. And it had all of these nice bounds all at once, right? But this was under the assumption of a sort of fixed tree or a fixed set of items. And also on the assumption of sufficiently many accesses to swallow the overall potential change. Right? We recognize that, you know, the starting tree may have very high potential, which in a sense gives you free work that you can do that doesn't actually properly measure the real cost of doing your operations. And so we had to sort of make sure that that free work was small enough to be negligible. And we showed that if you access every item, then the total amount of work that you're doing kind of dominates the error term introduced by this possible change in potential. But there's still this question, what about updates? So yes, it's nice to be able to search, but often you have to build the data structure first. You have to insert and delete. So we have to decide how we're going to do these operations on the display tree, and then what kind of cost is associated with them. Okay? So let's think about, let's see, what do we do first? Let's do insertion first. So how might you go about inserting an item into a display tree? So an idea would be insert, then display. It seems plausible. Just sort of to think it through, what if we inserted and didn't display? Would that lead to a good data structure, good algorithms? Sorry, I can't hear.
So the real world will be order 1, but the potential changes.
Well, would the real work be order 1? If we just insert and aren't splaying at all, before we even get to the potential, what might that do to the real cost of the operations? It could be as large as n, right? Right. So if we only insert in the usual way, we're going to be looking at a possible omega of n cost, right? Because the display tree does not do any kind of automatic balancing, right, if you don't display, right? And so we have an unbalanced binary search tree, which in the worst case could be a chain where you end up keeping on tacking things onto the tail end of a linked list. That would be unwise. So the question is, does inserting and then splaying address this problem? Yes?
Depends on how the potential function will change after display.
Yeah, so we know that display is nice when we are searching for items, but we have to worry about what's going to happen with the potential if we're inserting new items, right? And actually, I think this is the reason that people don't tend to talk at the start about insert as the sort of canonical operation for splay trees, because it's rather messy to think about the change in the potential. Okay? Because we don't know what the shape. Why is it hard to think about the change in the potential? Well, we don't know what the shape of the tree is, so we don't know where is this item going that we're inserting. So we don't know what tree sizes it changes, and so we don't know how it changes the potential of the tree. That's all somewhat worrisome. Yes? So how do we address this? Well, we actually, in splay trees, insert and delete are not taken as the sort of basic operations for updating the splay tree. Let me instead show you a pair of alternative operations. So one of them is split. Whoop, not splat. That would be fun. Split a tree T at a node X. So the split operation divides T into two trees, one of which consists of the set of elements Y that are less than or equal to X, and another one consisting of the set of elements Y that are greater than X. Okay. And the opposite of the split operation, join, takes a T1, an X, and a T2 with the requirement that X is between T1 and T2, and essentially creates the joined tree, the combination of the two sets. Okay. Actually, now let me give a more general join. Sorry. Let's create T1, join T1 and T2 with the requirement that T1 be less than T2, and creates the combination. Okay. So let's think about how to implement these two operations, and then we'll see how to do insert and delete using these two operations as primitives. And these two operations have very easy analyses from the splay tree perspective. So how are you going to do a split of a tree at a particular key X? Yes?
Display the node to the root and then take the left and right subtrees.
Good. So split. What we do is we splay T at X. And you say take the left and right subtrees. What do we do with the root?
Whichever one you want to be in, I guess.
Yeah, exactly. So since I've defined it to take the things less than or equal to X on the left side, what we're going to do is detach the right subtree. Yes? So now we have two trees, and we've separated the keys of the binary search tree. What about join? Do I need to do both of those things? Yeah.
Display the largest element as T1 and then give it a right child.
So splay the max of T1 and then attach T2 as root, as the right child. Why will I be able to attach T2 as the right child? It's a max, so it's not going to have a right child after the splay, right? Do I need to know what the max is in order to do this? No. What do I do? Yeah, I can hunt for the max without knowing what it is, right? I just descend, I just keep going down to the right until I get somewhere. And that is the maximum element. Yes? Okay, so now I have these split and join operations, which are actually pretty cool. It's not obvious how you could do a split or a join on, say, a red-black tree. Right? You have to think about that. So now, what can I say about the amortized cost? So we've talked about this a little bit before. We've had these cases where we are taking several data structures and combining them. And as before, we need to think about what that means on the potential function perspective. And we do the natural thing where we think of each data structure as having some potential. And when we combine the data structures, we also have to sum the potentials that come with each. But there may also be some potential that arises from the combination itself. Okay? So let's look at split first. Okay. What can we say about the amortized cost of splitting? Well, first we do a splay. And we know about the amortized cost of the splay. Right? Then what happens when we detach the right subtree of the binary search tree? Takes constant time, but what does it do to the potential? It lowers the potential, right? Right? Now, if you're lowering the potential, what is that doing to the amortized cost? It lowers the amortized cost, right? If the potential goes down, then you're actually getting some work that you can charge your real work to. So, so the amortized cost of a split is less than the amortized cost of a splay. Why is the potential going down? Where is the decrease happening? Yeah?
That's the new root.
The new root, right? The new root loses descendants. So its size decreases, and therefore its rank decreases, and therefore its contribution to the potential decreases. Now, does any other node lose descendants, size, potential? Everything else is unchanged, right? So only at the root is there a change in potential, and it goes down. So that's great. Okay. What about the join? Yes?
Are we considering the potential of, when you split, the potential of the two resulting trees, or just the one that still has X?
So yes, so when we're analyzing a data structure that involves sort of splitting and joining pieces, which is actually not uncommon in data structures, I mean, again, we've made up this potential function. It doesn't have real existence. But the usage that is consistent with wanting to prove actual bounds on runtime is to look at the total potential of the system, right? So when we do the split, now we have two trees. Each of them has some potential. The potential of the system is the sum of the potentials of the two trees. Okay. So what happens when we join? Well, if splitting decreases the potential, then presumably joining is going to increase the potential, right? So again, with the join, we have a splay first. But then the attach increases phi. Right? But by how much? Yeah?
I guess the root gains T2. So it increases by the rank of T2.
Root gains T2. Right? Well, remember, the rank of T2 is already part of the potential because we were computing the sum of the potentials of the two parts. So what changes in the potential?
The contribution to the root.
The contribution of the root, right? And how much does the root's contribution change? Yeah?
So exactly by T2.
So the size of the root increases by T2, which is less than our magic parameter n for the size of the data structure, right? And therefore, the rank of the root is still going to be less than log n. This is if we assume uniform weights. Okay. So essentially, this is the same order of cost as the other kinds of costs that we were looking at, right? So we gain, we have an increase in potential of log n if in the uniform analysis. And so that contributes to the amortized cost, a factor of log n. And so essentially, what we've shown here is, we do a splay to do a split, we do a splay to do a join, and then there's a change of log n in the potential. So split and join have amortized cost order log n. Now you can also go in and try and do, some of the other analyses become more complicated if you're doing splits and joins, right? For, what does access frequency mean if you're now going to be, so you can try and do that, but I'm going to focus on the uniform accesses analysis. And for that case, we've shown that you can do split and join in amortized cost log n.
Yes. The x we were introducing.
What happens to the what?
To x, like to the node we have added.
Oh, well, it's still there, right? So remember, the way we did a split, we're going to end up with two trees, one of which has no right subtree. X is in one of the trees. And similarly over here, when we join, well, there's no X to speak of here, but we're going to end up with two trees. We're not going to lose any nodes when we do the split or the join.
How did we insert x?
That's what I'm turning to now. Now that we know that we can do split and join, let's talk about how to implement insert and delete. So how can we do an insert using split and join? Yes?
So you split on the value you're going to insert, and then I would join T1 with the value you're going to insert, and then that gives you a new T1, and then you join that T1 with your old T2.
Exactly. So we split at x, so now T1 has all the things that are less than or equal to x. Now if x is already there, we're kind of done, right? But if x is not there, then in fact T1 will be less than x, and T2 will be greater than x. So now we can join x onto the right side of T1, and then we can join T1 union x onto T2. Actually, if we wanted to sort of go at it directly, we would just split at x, and then we would make x the root and T1 the left subtree and T2 the right subtree. Has the same effect, gives us the same change in potential. What about delete? Yeah?
You just split up x again and simplify to just join the two subtrees.
Good. So we split at x, we remove the root, and then we join the remainder. So very straightforward, right? And as we've just seen, that implies that we have order log n time insert and delete. Okay? So that's sort of the end of the story for splay trees. That now we've got them updatable as well. And I told you last time about some of the interesting open questions around dynamic optimality. Yes?
What about the change? What happens? Doesn't the potential change a lot when you do join T1x?
No, it does not. Right? That's what we argued right up there. Is that any two trees that we join, the potential changes only by log n. Sorry, did you want to refine that question, or?
What's the 90s upper bound on the amount of potential increase you can get when you add something to the leaves? Like,
So if you're doing the naive insert, I'd have to figure out what the sum from I equals 1 to n of log I is. It's probably not very nice, right? I'm not sure, but it is nice? OK. I mean, I haven't done integrals for years, so, you know, yes.
When we split at x, doesn't that mean that x is already part of t?
Ah, that's a fair question. So what if you split at a node that is not in the tree? Well, according to this definition, you'll just end up with two trees, neither of which contains x, right? And of course, you have to splay the proper thing, right? So what do you splay? If you told the split at x and you find out that x is not in the tree at all, what do you splay to the top in order for the split to work out properly? Yeah, and back?
The node that you get to when you're looking for x?
Right, which is going to be the predecessor of x, I believe, right? Or possibly the successor. OK. Good. Yes?
So this is the split, sorry. Insert delete only have order log in time amortized if we delete everything we insert.
No. So actually, once we start having insertions, we're in good shape in terms of the amortized analysis, because remember, the thing that we worry about is starting with a very large amount of potential and finishing with a very small amount of potential. But now that we're talking about inserts, we can say, OK, you start with an empty splay tree and you insert things into it. But that means we're starting with potential 0. Right? Our final potential is going to be positive. So in fact, our amortized cost is immediately an upper bound on the overall cost of the on the real cost. Okay. Let me mention one other interesting bound, just because it's kind of weird, to get at this notion of dynamic optimality, right? So I showed you sort of these sort of static optimality arguments, right? Like if you know the access frequencies, then the splay tree will access things with the entropy bound. Okay. Actually, sorry, a digression from my digression. Some people have used this observation to use splay trees as a compression tool. So one way to compress a series of symbols is to put them all into a splay tree, and to then look at the access path for each item as an encoding of the item when you're encoding a whole sequence of symbols. So the way you do encoding is you take the symbol, you find the symbol, and you report the series of lefts and rights as a set of zeros and ones that define the encoding of the symbol at that moment. Then you splay that symbol to the top of your splay tree, which means that if you're using the symbol a lot, you're not going to have to take a very long path in order to find it. And so its code is going to be very short, which is exactly what you want when you're doing encoding, is to have short descriptions of the commonly accessed items. Yes?
How does that compare to like Huffman encoding?
Yeah, so I'm not sure proving something about splay tree coding is kind of the same thing as addressing the dynamic optimality question, right? Because what you really want in a coding system is to have an optimal code for whatever it is that's input. And if you can prove that splay trees produce an optimal code, then you will basically have proven that splay trees are dynamically optimal. But for example, we showed this pi log pi bound, which is what you can get out of Huffman coding. So splay trees, I think, will beat Huffman coding for that reason. Okay. But here's another quick note about a dynamic access. One thing that has been proven, and this shows you the state of knowledge of dynamic optimality, is one of the most obvious things to consider is in-order accesses. So suppose I have an n-node splay tree. I go through the items in order. I access them in order one at a time. Okay? If you use a usual binary search tree for that, then since the average path length is log n, it's going to cost you order n log n to seek each item in the binary search tree. But suppose that you know that you want to visit the items of a binary search tree in order. How fast can you do it? This is actually true of any binary search tree, no matter what the shape. How fast can you get to all of the items?
Order of n.
Order of n. How come?
In order as well.
You do an in-order tree walk, right? So, so in-order accesses take order n time by a tree walk. You can prove that actually a splay tree also achieves order n, even though it doesn't know until it finished that you wanted to access the items in order. Okay? And the intuition is pretty clear that when it pulls up an item, it's also going to be pulling up the neighbors of the item, right? And so you're going to get to those neighbors faster than you would have if you left them where they were. Proving it takes some work. This is a strange place where they discovered some result in hyperbolic geometry that allows them to prove this fact. Okay, so if you like odd mathematical detours, you can go read this paper. I think it took a whole paper just to prove that it took linear time to access to do in-order accesses on a splay tree. All right, so that's the end of splay trees. I want to now move into our next topic. We've been working for a week now, sort of with our focus on the power of the potential function as a way to analyze data structures. But all of the data structures that we've analyzed have had something in common. They've been comparison-based data structures, right? We did Fibonacci heaps, which are based on comparing greater than or less than. We did this point location problem, which was greater than or less than for points and lines, but still based on this notion of computing greater than or less than. And now we have this Fibonacci heap data structure, which again is maintaining a sorted set of items under comparison. So all you have to be able to do is compare two items. Okay? And the comparison model is very general, but its generality also means that it is weak, that you can't make really great algorithms if all you are allowed to assume is comparisons. So the next thing that we're going to talk about for a little bit is bits. The fact that often when we're solving computational problems, the things that we're comparing are not arbitrary items with a comparison function, but they're numbers. And we can leverage the presence of numbers to do things better. Okay? And we'll still get to play with some potential functions, but we're going to do it in the context of this new idea. Okay? And we're going to start again with Dijkstra. Okay. Shortest path algorithms. So we saw how we can use a Fibonacci heap to solve shortest paths in order m plus n log n time. Right? And that was just based on comparing sums of edge lengths. But this is not always necessary. So sometimes your edges might be numbers drawn from a restricted set. So for example, how do we solve shortest paths when all the edge lengths are equal to 1? Do we build a nice fancy heap data structure and do delete mins and things? We just use BFS, right? Breadth first search. Okay. We don't really use a data structure at all. I mean, the graph is a data structure, but we just go through it one at a time. And what's the idea of BFS? Well, we've got the set of items that are at a certain distance, and everything that is at the next distance is a neighbor of the items at the current distance. And so we can just take all of the neighbors and simultaneously recognize that they are all at the next distance. Right? And so we don't need any order between them or anything like that. Okay? Well, let's try and generalize this. Okay? What if the numbers are 1 or 2? Do we have to give up the simplicity of a breadth first search algorithm just because we now have 2 different numbers to worry about? Or can we maybe keep some of that simplicity? Or even more generally, let's consider the case where the numbers are integers in a range from 1 to c. Okay. So the first exploitation, so how does this simplify our lives? And how might we hope to do better if all of the edge lengths are in the range from 1 to c? Yeah, I'm back.
Can we like split some of the edges into?
Okay. So one idea is to say that an edge of length L could be thought of as L edges. So we reduce to the breadth first search problem. Okay. So if we do that, if we take our graph with its short edge lengths and we transform it into this unweighted graph, this graph where all edge lengths have 1, what is the cost of our shortest paths algorithm, which is now just going to be breadth first search? C times what? So you claim m times c. Why? Yeah, go ahead. Good. So the argument is that each of our original edges, which might have a value as large as c, can get turned into, at most, c of these unweighted edges. So the number of edges increases by a factor of c. And so now we do breadth first search, and so we're linear in the new number of edges, but that is now mc instead of just being m. And so even if c is just a reasonably small integer like 50, you're paying a pretty big penalty to do this transformation. You don't have to explicitly do the transformation, right? You don't have to build the new graph. You could sort of you could implicitly represent the sort of part-way breadth first search along various edges. But it still does get kind of expensive pretty fast to multiply everything by a factor of c. So can we try for something better? Yes?
So for example, if we know that if we know C in advance, we can just have like C buckets, and every time we see an edge that has a value from 1 to c, like put it in the respective bucket.
Great. So let's unpack that a little bit. So there's an insight there that at a certain point in our shortest path algorithm, if we think in terms of Dijkstra, right, we've got a frontier. We found the vertices out to a certain distance. Now, the next vertices that we want to find, they're neighbors of the vertices that we've already found. So they're connected by an edge, and so that edge has value between 1 and c. And so the vertices that we're looking at next, they're only between 1 and c farther away, greater distance, than the vertices that we've already found. So you could imagine creating a heap, right, based on how far away they are. Yes? So instead of having a heap based on comparisons, you could have a heap that sort of buckets based on distance from the current frontier. Okay. Now, actually doing that directly is a little bit complicated because the current frontier keeps changing, and so you have to kind of decide you'd have to update all of the distances of all of the things in the buckets. But you just tweak that idea a little bit, and you get something quite nice, which is called Dial's algorithm. Dial's algorithm is pretty old. I think it's from the 70s, although I don't remember. And the idea of Dial's algorithm is to bucket by distance from the source. Okay. So Dial's algorithm just creates this nice big array. And probably, I guess, an extra thing at the end called infinity. And we're going to keep track for each vertex of how far away it is, according to our current measurements, from the source. So initially, we've got the source itself at position 0. And now in a Dijkstra algorithm fashion, we will go through and look at all of the neighbors of the source and say, okay, those neighbors are at a certain distance from the source, so we can put them into the appropriate buckets of distance from the source. Okay? So this array is taking the place of our binary heap. All right? And it's going to be a more efficient data structure for doing what we want to do. So we've just scanned the source. We've put its neighbors into the array. Everything else is still off at infinity. How do we now move forward on Dijkstra's algorithm? What's the next thing to do after you have scanned the source and updated the distances of its neighbors? Yeah?
Do the same thing for bucket one.
So, well, Dijkstra's algorithm doesn't talk about buckets, right? What does Dijkstra's algorithm say you should next do after you have scanned your first vertex? What's that?
Explore the neighbor.
Well, we've found the distances of the neighbors by this scan. What does Dijkstra's algorithm then say to do? Yeah? Extract min, right? The next thing to do is to find the closest vertex to the source. Okay? So that would in this case be x, right? So now we take out x and we scan x's neighbors, right? And so x's neighbors go into the buckets at various places, right? All right? And now we proceed, right? We need to do another extract min, right? So how are we going to find all of these mins if what we have is this array-based data structure? Yeah?
If you have only positive weights, you're going to progress linearly.
Great. And remember, Dijkstra's algorithm only works if you have positive weights, right? Dijkstra's algorithm doesn't work with negative weights. So that's a sort of an implicit assumption in everything that we're doing here, but you're absolutely right. So the algorithm for Dijkstra is to scan the bucket pointer forward to find the min. And then to update min's neighbors with new distances. Okay. So let's just unpack the runtime of this algorithm. Okay. And I've already broken it into two steps that it's kind of nice to look at separately. So we've got this scanning cost. What can we say about the cost of scanning over to do our delete mins as we're running Dijkstra's algorithm? Good. So the first thing that we can say is the cost for a single scan is going to be C. Why is that? Why is the cost of a scan C? Yeah?
Any neighbor is at most in this C from.
Right. We've just done one. We've just been sitting looking at one vertex. Okay. But we have to be a little bit careful. What if the vertex that we just looked at doesn't have any more neighbors? Yeah?
The next neighbor is like a neighbor of something that came before. So
Exactly. So if it's not a neighbor of your current vertex, it's a neighbor of a prior vertex. And the prior vertex had even a smaller distance. So a fortiori, the neighbor of whatever it is going to be within C. Right? Now, there's another way to argue this, which will actually be convenient for later. What can I say about the cost of all the scans together? Okay, so one way to talk about the cost of all the scans is to say that I'm going to do n scans, and each of them has cost C. So that's a cost of nc. But I can make a more direct argument if I'm thinking about all of the scans together. Yeah? M. So how M?
The number of updates is the n.
So that's actually going to be relevant when we look at the second half of this algorithm, when we talk about updating neighbors. But right now, I'm just talking about the scans for the delete mins. And I want to bound the total work of the scans for the delete mins. Yeah? What's that?
Oh, the array is only in maximum.
Good. So the argument is that the maximum distance is NC. Right? The farthest you can be from the source is NC. And the scan is linear in your maximum distance. Right? So it doesn't actually matter how much each scan costs. What matters is that over the course of the algorithm, we're just going to be scanning this array once. Okay. All right. What about the other cost? What about the cost of updates? So I hear claim of M. How come? What's involved in an update? Yeah?
Every time you do an update, you're like going through edges and you never use an edge more than once.
Good. So when we update one edge, what's involved in doing an update for one edge? Well, you look at its current bucket, and if you don't like it, you move it to a different bucket. So it's constant time to move a particular vertex at the other end of the edge from its current bucket to a better bucket, if you should. Right? And then you just observe that each edge is scanned once, which is sort of a fundamental feature of Dijkstra's algorithm. That's why we prove that Dijkstra's algorithm is order m log n. So the total cost of updates is order m. And so putting this all together, we find a total runtime of order m plus nc. Pretty nice. Questions? Yes?
If there are more than one nodes in the same bucket,
Yes?
does that affect the runtime?
It's a fair question. Does it? I'd like to take a stab at answering that. Yes?
You can pull one out arbitrarily, so you can do that. It doesn't matter which one you choose, so you can pick one out.
Exactly. If you have multiple nodes in the bucket, you just do them one at a time. Right? Essentially, you're saying the cost to scan to the next node is 0 because I'm already at it. So I just update each node in the bucket. Right? And all of that is in the update cost, the order m update cost. It doesn't add anything to the scan cost, which we've just total bounded by order nc. Okay? Other questions? All right. We haven't asked the only question possible about this algorithm, though. What about its space usage? This actually, in many modern algorithm designs, space matters more than time. Right? If you can fit something in main memory, it runs fast, and if you can't, you're dead. So what can we say about the space usage of this algorithm? Yeah?
So you really only need to maintain a window of C.
Good. So that's where we're going. But before we get there, what's the naive space usage? Naive space usage is NC, right? We have this giant array which goes up to the maximum distance. Right? So the naive space usage is NC. But now, as you're saying, we can be a lot cleverer than that. We can recognize that at any given time, we only need a window. How big does that window need to be? Yeah, it's a window of size C. Or let me be a little cautious and make it C plus 1 so that we have a difference between 0 and C. Yeah? OK. So here's a kind of a nifty way to do that. If we're thinking about that giant, we want to simulate that giant array, but we know that everything that is relevant is going to be in a window size C. So we can simulate that array by basically doing clock arithmetic. We will just make an array of size C, but put it in a circle. Size C plus 1, rather. And so we'll say we have our numbers from 0 up to C. Right? And we'll use this array. We'll put, S will go here, and its neighbors will go into various places. And we'll scan bucket 0 and update neighbors. And eventually, we'll be finished with bucket 0, and we'll move on to bucket 1. Well, once we've left bucket 0 behind, we can start using this bucket 0 as bucket C plus 1. Right? And as we move the scan forward, we'll just keep recycling everything that was behind us to be used for a different number. And essentially, at any point in the operation of the algorithm, each entry in this circular array corresponds to exactly one number. There's no ambiguity about what number it is. Okay? And so that reduces our space usage to order C, which is, of course, far superior. So that's Dial's algorithm. Pretty simple, pretty clean, using only an array as a data structure. But that use of an array is what really differentiates this algorithm from all of the algorithms we've seen so far. So all the algorithms that we've seen so far have been based on comparisons, and they've been based on pointers. Right? So our heap has pointers to a specific set of children. Our binary search tree has a pointer to a smaller item and a pointer to a larger item. And in fact, there's a lot of work in data structures studying what can be done if you only have pointers. If the only thing you can do is allocate a node of a fixed size and set pointers within that node of fixed size to other nodes. And there are bounds on what pointer machines are able to accomplish. Yes? Yes? Sorry, say again?
How do you put vertices in a bucket?
Oh, well, I'll just keep a linked list off of the bucket.
So why object is equal 1?
Well, the thing to remember is that I don't actually care about the order of that linked list. Sorry, I should make it a double linked list. OK, so what are the things I need to do? I need to put an item into a bucket. I need to take it out of a bucket. So if I have a pointer to the item, and it's in a doubly linked list, then it's constant time for me to splice it out of its current linked list and insert it into another linked list. Okay? And I mean, I'll have those pointers. This is sort of part of, each edge will point to its neighbors, each vertex will point to its position in the bucket, and so forth. Yes?
Was that not?
No.
Sorry, yes, red shirt.
Oh, okay. So let's say like the first thing you access has n nodes in it. Like, so you basically have a linked list of n.
Yeah.
Does that not increase your space size to OC plus n?
Oh yes, sorry. There's certainly an n as well for the nodes of the data structure. It's not, you're not literally using constant space, right? But the point is that in addition to the nodes themselves, you only need C. Yes.
We need the plus 1, like the 0. Is it like
I'm just being careful so that nobody can catch me on anything in class, right? I hate it when I end up being wrong. So this way I'm being conservative and I'm safe. Okay.
If I add the point at the source, I might be confusing, like losing track of which step I am in the. I'm talking about the circle.
Oh well, I'm going to remember which step I'm in, right? When I add the point at the source, I'm going to say my current distance is 0, and that corresponds to this position. Right, and I'm just going to keep track of that as I go. And obviously, if you really need to squeeze out that extra 1 unit of space, I'm sure that there are ways to do it. Okay, but I'm going to be lazy. Okay. Yes.
I have a general question. So whenever algorithms involve numbers,
Yes.
like the space for the number to store that number is large.
Very reasonable question. Right, so what I was saying before, pointer machines, right? We talk about pointers and pointers to other nodes, and I mean, a pointer takes up space, but it's kind of implicit in the model. Once we start talking about integers and about RAMs, you can ask, do I care about the sizes of the integers that I'm storing in the RAM? Okay, and the kinds of operations that I'm allowed to perform on a number that's in a RAM. So some RAM models allow you to store integers of arbitrary size in each position in a RAM and do things like add 2 of those integers in constant time. And it turns out that if you can add infinite size integers in constant time, you've got a pretty powerful machine. And you can solve a lot of problems really fast, right? We're not going to go for that amount of power, right? Sort of in all of the problems that we're studying, the sizes of the integers that we're dealing with are going to be limited to, log n bits. They're going to be polynomial size integers. And it's standard within these RAM models to posit that you can put log n bit integers into each word of the RAM. If you want to be picky, you can look at RAMs with constant number of bits, or look at bit RAMs. You know, there is that log factor that we may have to worry about, but again, thinking about a standard, an actual machine, they have registers, they can, you know, we tend to think of the number of bits that they have as the log n that we're interested in. Okay?
So we tend to ignore those things in the complex.
That's right, that's right. So in these RAM models, we assume that you can access anything in the RAM in constant time, which is what a pointer machine cannot do, right? With a pointer machine, you need some sort of structure, a tree over all of the nodes in memory, and it's going to take you non-constant time to reach a node based on its address. So random access gives you this extra power to do something in constant time that's difficult on a pointer machine. Okay? And the other thing that we're using in Dial's algorithm is indirect addressing, right? That we're sort of picking a spot in the RAM based on the value of an integer. And that's what allows us to do Dial's algorithm so fast. Okay. So that finishes the story of Dial's algorithm. The next thing that I want to do is refine it, make it more powerful. But before I do that, I think that we might as well take a short break just to let people stretch their legs, because this has been a relatively dull lecture and people are probably falling asleep. So get up, do some jumping jacks, talk to your friends for a minute, and then we'll come back to some more material.